So what I want to do is quickly just go through the stuff that we've gone over this year formula-wise, so you're all clear as to what you're going to be expected of. On the first chapter of the year, we talked about just basic kinematics, and those are our starting formulas here. So what I want to do today is simply do this, because if you have a formula sheet or a reference sheet, that's all you really need in physics. But you have to understand what these mean. Without knowing what they mean, these are pointless, right? Like, I mean, if you don't know what this equation means here, that's work, you're not going to know actually that, okay, F is 4 is d is distance, cosine of theta, theta is the angle. So you have to know what they mean to utilize them. This is the formula sheet that I'm going to give you on your final exam. Okay, this is the actual formula sheet that I use. There was the actual multiple choice section last year. Okay? So this is going to be your constants and stuff that you need also. You're not going to need C actually, because we didn't get to that. That was the last thing we didn't get to. No big deal.
So we were behind?
No, we did a lot more in depth. I'd say that we didn't do maybe 1 or 2 major topics at the end. That is like another like week worth. But at the same time, we went a lot more in depth with the stuff we did do. Teresa. Sure, that's fine. I think I gave you guys, though, a lot of the answer keys throughout the year. I would either give you a student solution or your own. Okay, I'll look, Teresa. Some of them I didn't make answer keys for. I just did it myself as I went through, so I don't have one for them. But the ones that I do have, I'll put on there for sure. Okay, absolutely. First of all, these are good things to study. So if you want to, let's talk about what you should be studying from. And I'm going to talk about this again, especially for those that are taking the AP exam right now, but we're recording so they can at least watch what they missed. Some good things to study from on the test, or before the test. All exams, for sure. Okay, that's one of the things that's really good to study from. Sorry, so it's for my final.
Your final?
Let's put DVCR final.
The finals are 1.5.
It's final?
Okay? So your final is going to be during finals week. Your finals this year are 2 hours, okay? 2 hours long. So make sure you're prepared. It's a cakewalk, though, considering if you took an AP exam. Okay? It's 2 hours straight. That's what it is for your final.
1 hour and a half.
It's 90 minutes for when you're freshmen, sophomores, and juniors. When you're seniors, they're 2 hours. Okay? College finals are between 2 and 3 hours. That's why they do this. Not just to make you guys work harder. To make you prepared for it.
You mean all tests?
So old exams are tests, yes. Okay, labs for sure. Look over your old labs, please. A lot of the questions I pulled last year were from lab questions. Let's see. Homework questions. I would say that homework questions encompass maybe a quarter. I'll give you percentages in case you want.
Have you already?
Yeah. That's what I'd be at so far. Okay. And I'd say the last 15% is a mix of like classwork questions, so things that we've done in class. Oops. And then major discussion in class. So, for example, we don't always have things on the test that we've discussed in class. So things that I've mentioned in class, just because they weren't on your older test, doesn't mean it's not going to be on the final. So like we talked about random stuff at one time. Like, for example, why is the Earth warmer in the summer than it is in the winter? What does it have to really do with? That's the tilt of the axis, you remember. It has nothing to do with what?
How close you are.
How close you are. It's the opposite, right?
Mm-hmm.
So when you're closer to the sun, we're actually in the winter. When we're further from the sun, we're in the summer, which is the opposite of what people think. It has to do with the 23.5 degree tilt of the axis, which is where the Tropic of Capricorn and Cancer come from. If you look at, remember the Earth when you were younger, you studied the globe, okay? You had your North Pole ring, you had like the South Pole ring at the bottom. Through the middle of the Earth, we call that the equator. Then there were these other 2 lines that most people don't realize that exist. The Tropic of Capricorn and the Tropic of Cancer. They have to do with the tilt. 23.5 degree tilt is where those lines come from. So here, this is 0 degrees latitude. Up at the top is like your 90 degrees latitude. This is your 23.5 degrees latitude. Okay, that's the tilt of the axis that has to do with that. So these are like random things that we've talked about. You don't need to know these numbers at all, but the idea of the theory. Okay, the theory. This is leaking hardcore. Yeah, it's going on. So the ideas behind what we talked about. What did we talk about for like a black hole? What's the idea behind a black hole?
How, people think that black holes.
Way too hot, way too hot, I'm
Oh
sorry.
my gosh, I thought you were about to say
Yeah.
How people think that black holes are like time travel, whole time, but black holes are dead star.
Good, stars collapse on itself. Very good. Why is it called black hole?
because it sucks up all light. It's a light.
Then it sucks up all
It
the.
sucks up all the light. Okay? It's the absence of light there. The absence of light.
All this random
So that's the last 15% I'm saying, like classwork questions that we talked about and discussions. Oh, definitely. What about, for example, like we talked about how a refrigerator works in class. It takes out the heat out of the refrigerator. So you have this fluid, the fluid that runs across it. When we drew the box, the fluid that's a cooling fluid that absorbs the heat. The heat comes off from the bottom of the fridge, you feel it on your feet, and then it goes back through the cycle again.
Will these questions like this, write them out, it would be like.
You're gonna have this exact, I will never change format. We do one thing only, it's not
So
gonna
it'll be
change.
like a brief.
Multiple choice, short answer, mathematical free response.
We
Exact
got
same
cheat
thing.
sheet.
I don't know. Last year I gave just a formula sheet on the test. I actually gave one. I'm tempted to do like an index card this year. If I do something, it would just be an index card, so I don't know.
But it's 2
Can I
hours
do it for a
long.
winter?
We should get that.
I give you guys an index card? Yeah,
But, is it going on the whole year?
whole year. It's just like math, guys, cumulative, not cumulative. The reason being is this. You cannot, sorry, where are we? Where's the formula sheet? You cannot ignore the stuff we did in the beginning of the year because it comes up again when we did stuff like forces and momentum. Velocity is used again. So by default, physics is a cumulative course. It's not like you end a chapter and the next chapter doesn't matter or the older chapter doesn't matter anymore. You use all the stuff from velocity. You use Fg, right? Isn't this the weight of an object? Didn't we also use that for buoyancy? We use the weight of the object there. So you can't ignore what we did at the beginning of the year. By default, it will be on there. Okay? And there will be an equal amount. It's not going to be like some teachers do, like most of it is the second half of the year and only a little bit from the beginning. It's going to be equally spaced. Okay? So study all of your tests. All of your material in general. What was I saying before that question, Karen? Black holes, refrigerators. Oh. And then you show it on the TV. The format. So you could expect. Well, I can tell you right now, multiple choice wise, exactly how many problems because I have it. Multiple choice wise, you're going to have 32 problems. Okay, 4 choices per problem. Each of these problems is worth 2 points, same as your test. Each of your short answer worth 3 points, same as your test. 2 points for multiple choice, so 32 problems. Let's see. Okay, 32 multiple choice at 2 points each. I don't know the exact number of the other two without looking, so let's see. Short answer, free response, my guess before actually going back. I think there's about 10 free response. Those are the math ones at the end of the test, worth 4 points each. Okay, there's about 10 of those, I think. It's probably about 15 short answers, worth 3 points each. It's a long test, guys. It'll take you the full 2 hours. Okay, but everybody finished last year. But a lot of people finished with like 10 minutes left, and then others went right to the very end. But for the most part, you'll get through the whole test. There's just a lot of thought processes that's going on. The hardest part for some people, honestly, was just remembering how to use the formulas. That was the hardest part. The theory part, the short answer, everybody did really well on. A lot of you guys do well on that. That's good. So you want to make sure you understand the ideas. Okay, but then how to apply them mathematically is really where you're going to use physics tonight. Okay, you can't just know ideas and not know how to use them. Like you could know that I weigh a certain amount and that there's a normal force pushing back up, but what good is that going to do for me if I can't apply it to like cars, if I can't apply it to airplanes or buoyant force? Okay, that's all mathematics.
I'm saying no, it's backwards. I don't know if theories are how to do mathematics.
No, I know the theory about that.
If you know how to do it mathematically, you know some of the theory by default. You have
Yeah,
no
I
way
know
to do
yeah.
it, but you might be better at mathematics, I'm sure. In college, you can take courses in physics that are either math-based or conceptual-based too. If you study some sort of science or math or engineering field, you'll end up taking the mathematical-based physics. So you take a physics that is really mathematical, so you're looking at, you might have calculus involved. You do the stuff that we've done with the free response mainly. Whereas conceptual based physics, which is physics you might take if you're like, say you're an arts major, or you're a business major, or you're a nursing major, okay, majors that are not necessarily science-based. I know nursing is science-based, but there's more conceptual in nursing. You'll take a course that is like, they might call it university physics, which is like the ideas and the theory behind it. So it's going to be a lot of written work. So for example, you'll learn about maybe the history of a lot of physicists. You'll learn about where the ideas came from. You might learn about planetary motion and astronomy, but you have to answer with words. You can take for college. You can take courses in astronomy. You can take courses in dynamics. Okay.
No bad Martin.
You can take other ones also.
When we learn this.
And I'm just discussing the way you can use this. That's all. All right, let's go back to the formula sheet. So let's quickly discuss, and I'm not going to go into example problems yet. I want to go through the formula sheet, and then maybe next week during our review we can look at that. This will help for your Crystal Ray ones. I'm trying to go over the ideas.
Yeah, I remember all of them. Now, I remember most of them. Like, I know the first part is like for motion. We did motion.
Good. So let's use what Julian just said. Let's use what Julian just said. Why is this not working today? Yep, that's what we're going to do. All right.
Alright, the first part was the motion.
And how many directions? Good. One or two, really. Remember, at the beginning of the year was one-dimensional motion, an object moving back and forth. And then eventually went into projectile motion. So this is motion. Very good, Julian. Now tell me what some of the variables mean.
Alright, V is for velocity.
V is for velocity. Okay,
V
good.
is for distance or displacement. That's distance, okay.
This is for displacement.
And T is for time.
Let's put X here for now, guys. Let's put X. I'll change it on yours. Last year we used D. Okay, T is for time. Very good.
And A is for acceleration.
Okay, A is for acceleration. Yeah, I'll definitely give you a copy of this next week. So if you want to just write down notes for now, no problem. I'll give you a formula sheet so you can see. All right. What else? Next formulas. What are those used for? See the next three? Because the first two are obvious. The first one, it's velocity, displacement, time. That's what you're going to use. If you have an object moving and you want to find its displacement, you can know its velocity and time. What are the next three used for? Yeah, so these are finding those problems like where we have a projectile launched, and it says it goes a distance of 200 meters. And you have to do the y direction and the x direction and split it up into two categories there. Okay, so this stuff right here, this right here, is where you're searching for the beginning or end of a problem, or some characteristic about the problem. It's more specific.
And that's when you take the whole page to do one problem.
Yes, these are the long problems. Right? So this has to do with a lot of, we can do 1D motion, but it was mainly used for 2D motion. Okay, two-dimensional motion like projectiles. And it was more specific. Okay, these problems are like, find the distance traveled if you have the initial, the final, the acceleration, the time, very specific problems. Whereas these are very general problems, like a car travels 200 miles in 5 hours. What's the velocity? 40 miles per hour. Okay, that's like very basic stuff up here. You could expect to use these ones in examples that are like multiple choice, you know? If there's a multiple choice problem, you might need to use these. But these you would use for like your free response, for an object launched at a certain angle, okay? What about, in this part, we also looked at theta, and it's not in the formula. But where do we use theta?
Oh.
Cosine sine.
Yeah.
Okay? Running out?
I don't.
Hold on, let's go Byron and then Julian.
Yeah, we put them if there was an angle, and if there wasn't, it would just stand zero.
Very good. If there was an angle it was launched at, we use that angle. If there wasn't an angle, it was just zero, really. Okay, but what else does it have to do? What are we doing with these kind of problems when there's an angle?
Oh, yeah, add on, like what you do is, if it's shot at the angle, you have to add on to the angle, because remember, we had the thing, where like the angle would pull, like the boat was put at an angle of theta. Then you have one side, like 30 degrees, you have to find theta.
Force. Are you increasing the force? Like, we are talking about, can you repeat your?
You guys are answering with good ideas, but I wasn't even asking that involved. All I was asking was, for 2D motion, where does the angle come into play? What do you have to do if it's launched at an angle? Break it into what?
Oh, two parts.
Yeah, components, that's all. Yeah, I mean, you can use force, and what you're saying is right, but that was like with the example of the boat and the current of the water moving. Those have angles also. But for this application here, okay, this was just a launch angle. Launch angle, theta, okay? So if you wanted to find the x component, what did you use? Which part?
Wait, X.
X component.
Cosine.
Cosine. The y component was sine.
Oh, yeah.
Okay? The only time it was reversed was on an inclined plane. Remember inclined planes? We switched cosine and sine. It was the only time. Only time. Okay?
But I thought you were supposed to use, what, X, I'm just trying to use, oh, never mind, because cosine 90 minus theta is basically sine.
Yes. Very good. Very good. It's a complementary angle.
Alright.
Now, Fg, what did that represent really? Force of gravity. What do we also call that? The what? It could be the equal as normal force. It could be equivalent, yes.
Oh, wait.
The weight. Again, Fg, guys, Fg, you're going to see it as Fg because if I put W there, some people might think work. And work comes into play down here, okay? Fg is the weight of an object, mass times gravity. Now, if I'm standing here and my weight is 200 newtons, whatever Newton value it is, what's the normal force?
200.
Right? Because I'm at what?
Equilibrium.
Equilibrium. I'm at a state of equilibrium. If I'm on an elevator, though, like in this example, you put a scale on the elevator kind of thing. You're on the elevator and you're moving down fast, or you're accelerating downward, you might feel like you're floating a little, or you feel like you're way less. So the normal force goes down. It's like when you go to Six Flags, if you're going tomorrow, and you go on any of these free fall rides.
The drop zone.
Okay? Is the drop zone one of them?
And you go like,
Yeah. You're going to feel weightless. I'm going.
I'm going.
I don't go on rides. I'm going. You feel like weightless. When you ride
What are
it?
you gonna do?
I played a lot of games last year.
No,
Came out of I just don't, I get really sick. I went on rides before and thrown up all over the people.
I'm getting on the king.
Oh,
Yeah, I will not be closed. Last time I was mad. I gotta give this a big.
I'd be mad too, that's why I don't go on rides. I don't want people to get mad at me now. I do not want to get sick, and I get real sick.
You should just get it back. You know, or you can just not ride.
It's not fun.
You should get it back.
I've done it 3 times, and God, 3 times in my life, and thrown up every time.
You need to go in and sing team.
But water rides are totally good about it. Like theme parks, like, oh no way, that was the worst thing ever. Spinning in circles, that is also spinning in circles.
We got wet on the ride.
But if you guys like water parks before, like actual water parks, those I love. I don't have any problem with those. At Six Flags, is there a water park?
No, yeah.
I've never been there. I've been to one in like Florida. It's called like,
The W word?
I don't know. But they have like another park over there, like water or something.
Yeah, hey, Universal Studios there, 3 days.
Something
Disney,
water, it's like something.
Disney, then you got Universal Studios, then you got the water park. Yeah, that's a big park.
Islands of Adventure.
I've been there. Harry Potter was there.
Yeah, I got them at. It was alright.
I thought the theme park, the theme park was better than the ride itself.
Yeah, the actual like cast.
Yeah, that was the cool one. Alright, so next one, friction. Friction. The force of friction is proportional to the normal force. And think about it logically, people. Ready? Here's your most basic example. If I want this eraser to stay against the wall, what do I have to do to it? Push it. So the wall is pushing back with a normal force, right? So if I push harder, the normal force pushes back harder. So now there's more friction. But as I lessen up my force, what's going to happen? It's going to slip because there's less normal force coming off the wall. It's like, if you've ever done this before, have you ever tried to carry a laundry basket while carrying something else. That's
Yes.
full. Ever take a laundry basket, kind of like tuck it under your arm, and you press it against your chest? Why does that work? Because you're pushing against your body, which is pushing back with a normal force, thus creating friction. That's where it's staying on you. So if you let go, it's going to fall. Yeah. Or if you hold one of your cousins or your younger siblings, you hold them under here, right? Because you're pulling them. You're pushing with a force, which is pushing back with a normal force, which provides friction so they don't slip out. You went like this, what's going to happen? They're going to fall.
I don't want it.
Babies are awesome. No, I mean, obviously there's parts about babies that are not fun. You know, like crying a lot. We were at, remember the little kid we saw yesterday at the theme park? At the farmer's market? The little kid came to the farmer's market and said it was adorable. Hysterical. Real funny.
No kid is cute. They came up here and told us y'all
Michelle singing.
Alright, so the value of mu here, okay, the value of mu is a material property, if you remember, okay? Material property because, think about it, sandpaper on wood, isn't that pretty hard to move back and forth? Whereas if you have like ice, a piece of ice on metal, it would slide, right? So mu, as mu gets higher, there's more friction, okay, because it's proportional. As this goes up, this must go up. So whenever you need more friction, you have to have some sort of a coarse surface. You want coarse-grained surfaces. That's why you use sandpaper to get rid of the pieces of wood that are not very smooth. Okay, you smooth it over because there's a lot of friction. What kind of friction can you have? There's two types of friction.
kinetic and
Kinetic and static. Very good. Well, still. Well done. Moving and not moving. Now, remember, if an object is sliding across the floor, you have to use the value of mu k. If an object is at rest on an inclined plane, and you want to know how much friction is holding it there, mu s for static. Remember, mu s is always bigger than mu k, and that's logic. If I wanted to move this, isn't it harder to get it going than it is to keep it moving? Once you get it going, it's pretty easy to keep something moving. It's like furniture if you ever move. To get the furniture moving, you got to give it a nice push. Once you get it moving, it's pretty easy. Static friction is hard to overcome. Okay, always, always, always. All right, next. W equals FD cosine theta. F is? W is work, sorry. F is force. Sorry, D is distance traveled. Cosine theta? Good, that angle between. Okay. What are the units of work? It can't be work. Force is a Newton. Joules. And the reason we know this is because if you remember the work kinetic energy theorem, if you apply a certain amount of work to an object, it gains speed, doesn't it? So it gains kinetic energy. And kinetic energy is in joules, so the joules and the work must balance out in a sense. Okay? So again, kinetic energy is moving energy, V is the velocity, M is the mass. What do we use this object example? Very basic example. An object falls off a cliff and it falls a distance of 30 meters. If you know the potential energy at the top, it's equal to the kinetic energy at the bottom. So if you want to find the velocity for a problem like this, you'd say mgh, the potential energy, equals 1/2 mv squared. Okay? So what do you notice about the masses?
cancel.
So the velocity of an object after it drops is completely mutually exclusive from the mass. It does not depend on the mass. Who's in statistics in here? Have you heard mutually exclusive or non-exclusive?
Yeah.
Okay? Mutually exclusive means they're not related, right? They're independent. Whereas dependent outcomes in statistics depend on one another. Like if you want to roll a 3 and a 7, if the first die is a 3, what does the second one have to be? A 7. Okay? So those are dependent. These are independent of mass. The mass has no effect on the problem. Okay? No effect on the problem. What is this one? Where does this come from, guys? Of what though? A spring. A spring.
Why did you put
Okay. That's fine. Again, a spring. How do you know it's a spring though? What gives it away? K. K is a spring constant. The only other time we've seen K has to do with our thermal conductivity, conductive, convection, radiation. Okay, those three. Which I need to add. I don't know why that should include them.
What is the K mean? Because that means we didn't know words.
Okay, I gotta add those three then. Yes, exactly. K is a material property. It's the stiffness of the spring. Think about a spring, guys. You take the spring out of your pen. Okay, its K value is very low. Look at the spring on a car. Its K value is very high because it has to withstand that mass, that constant mass of the car that's pushing it up and down. Okay? So the spring stiffness, another word is rigidity. Rigidity.
Oh, that's the word.
And that's the K value. What is X again?
X, but it's displacement.
But it's the displacement of the spring has been what?
Compressed.
Compressed or
After release.
or
No, compressed and decompressed.
which is called stretch, what you were saying. Either, again, X. If this is the spring normally, and the spring is, let's say the spring is normally, they're cutting the grass. The spring is normally 10 inches long, and you compress it to be 5 inches long. Or, you compress it to be 3 inches long. How far have you compressed it?
What did you say the first number was?
7 to 3.
4.
Oh,
You said 10.
I said 10, I give you the answer, right? That was what I said.
Stop it.
If you go from 10 inches as the free length of the spring, and the spring gets compressed, so it's about to launch an object until it's 3 inches. The compression is 7 inches. That's X there. Remember, X is the amount that the spring has changed. So what should it really be considered? It should really be a delta X. Okay, a delta X. Yeah, I'll change this to delta. Okay. So I'm trying, the reason I did these is because that's the way they appear in your book. But the way we've used them this year is much better, so I'll change them so we know it's short.
Can you take a picture and just put it like that?
He's not just
I'm just gonna fix it.
You gotta take.
I mean, this is also on the recording, so you can just skip to the video at this point. If you for yourself, but I'm just gonna go on and change it. What did this P have to do with now? Power, there it is. Again, work over time is power. We did not use FV this year, so don't worry about that, okay? We used work over time. Work over time. The other thing that we did do was remember, you know what? Don't worry about it. It's not going to be on there. It's all right. So, lowercase p. What's low? Right. What is it?
Power.
This is the one that does not make sense. This capital P here is pressure. Okay? Pressure and power are both capital P. What was lowercase p? It's not density, that's rho.
No, it's, I know it. Density.
What is it?
It's not, bro.
Oh my gosh, I know that.
Now, again, this is momentum here. Okay, and think about it logically. Here's how you can remember this. Look at the formula. Think about it logically. If you pick up more momentum, either you get bigger, right? A bigger person has more momentum, or you speed up more. We did the examples, very good. We looked at like 2 videos with football players. Okay? A football player has more momentum for 2 reasons. Either he's bigger or he's faster. And that's why running backs can knock over linemen. Why do you think they can break tackles at defensive ends? The defensive end might be like, 285 and huge. But the running back is running with a velocity that overcomes the momentum of the defensive end, therefore knocking him over.
But he's not moving though. So
They're both moving. The defensive end is moving to tackle him, but maybe not as fast, because the defensive end is waiting, right? He's waiting for the tackle. Whereas the running back is picking up speed or velocity, so his momentum increases. That's why he can run him over sometimes. Okay? People say he's more powerful. It's not really more powerful. You have more momentum. Okay. Also, the example momentum. Remember the pool table. Pool table is a good example to use. Pool table is a good example of transfer of momentum. If you hit the cue ball, the cue ball hits, say, the 8 ball, and say you put, you know what English is? Backspin. Say you put backspin on the cue ball. You hit the cue ball, so that when it hits the 8 ball, it stops, because you don't want it to follow into the pocket. So all the momentum of the cue ball hits the 8 ball, and it's transferred into the 8 ball. It's a balance of momentum. Okay? We did it with, very good. And the next one is the same with trains. Remember trains. The trains can either lock together, or it can hit the train and push it off. That has to do with inelastic versus elastic collisions. Inelastic versus elastic collisions. This all comes about here too. This is your key, the last one. The momentum before equals the momentum after. Okay, what do we call that when something equals it before and after? Transfer. It's a transfer of momentum, in this case, energies later. But what is it called when something does not change or lose or gain value?
Oh.
Close. Constant is perfect, that's fine. But it sounds like constant.
What is
Conservation. Remember, conservation of energy means energy cannot be created nor destroyed. Conservation of momentum is the same, but it has to do with momentum. That's where this formula comes from right here. Okay? If I have a certain amount of momentum, and I run over and knock James over, sorry James, and it causes me to stop, all the momentum transfers into James. What are you going to do? I'm going to fly over. So I miss James, and I run to the desk. So the momentum hits the desk, right? Which causes a force on my head, which gives me a bruise. Okay? So remember here, where does this formula come into play? This is impulse. Okay? If you remember, we did examples of if a baseball bat, a player throws a ball, I hit the ball is in contact with the bat for maybe 0.5 seconds. That's the time. Okay? If you know how much momentum has changed, you can find out how much force has been applied to the ball. Okay? Alright, next column. I'm going to erase the ink on this page. Okay? It's a video, I can see it, don't worry. Or you know what I'll do? Here. Where's the copy? Okay, so it's still there. Just give me a different slide, okay? But I need to write, okay? All right. Next category. Notice what I'm doing, by the way, guys. Have you figured out with these boxes how they're? Yeah, they're in order and they're grouped. Look, 1D motion. No, this is the formula sheet right here. I think I did it in order, actually. I think I actually did, because I went from beginning to end through all my notes. But yeah, it could be. The thing is, Karen, the stuff that you do at the end of the year, also use it, the stuff in the beginning, so you're going to have to go back and forth by default. It does, yeah. Velocity, okay? Mass, density. It is really, though. Look, the buoyant force is mg. Well, that's mg from over here, really. It has to do with the gravitational force. So what is this category, guys? Let me give you a hint. What is this category? Circular motion. Okay, circular motion. Whereas this down here was momentum. This was work and energy. This was forces. This was 1- and 2-dimensional motion. Okay, they're categorized like that. Now, let's go through them. AC, not air conditioning. What is it?
Centripetal something. Acceleration.
Very good. Centripetal acceleration. Remember the example with the cups in the cafeteria. Okay? The lab that we do with the cups in the cafeteria.
Oh, yeah.
Think about what happens, okay? Think about what happens to solve problems. Why did the object not launch off? Because the tension, very good. So much force in tension, very good. The rubber bands provided that tension force there, which is why they ended up stretching out, right? Because there was a lot of force on it, which caused them to act like a spring, like Hooke's Law the other day. Those rubber bands were really a spring. When you spun it faster, what happened to the spring? Stretched out because there was more force. And you remember Hooke's law? Hooke's law tells us F equals negative kx. More force, it stretches out more. That's where that worked. Okay, that's why that worked. What else? FC. Centripetal force. Okay, centripetal force. Again, V squared. What was V again? And don't just say velocity, because I know you're all going to say it. This is a tough one. What is V?
Variance? V and volume.
Yeah, what is it, Karen? Tangential velocity. Tangential. What does that mean, tangential?
It's like on the edge.
Very good. Again, the velocity of the object in that direction. This is the tangential velocity.
That's the thing you do.
Yes. Good memory, sir. Remember the keys? If I let go of the keys, when it's going towards you guys, I'm not going to do it. If I let go when it was out there, it would shoot at, pretty much like Taysir or Danae, toward the back. If I let go of it when it's in the front, it would move tangential that way. So remember in the front, it went that way. Okay, so take one of the door. So remember, wherever the object is released, it goes tangential to the motion. Put that one under the door. All right, the next view, where do these next ones come into play? Gravity, right? Gravitational motion. So, planetary motion.
Yeah. And there's like an escape
Planetary, AR1, I think. Okay, again, let's discuss quickly. If you want to find the force of gravity between the moon and the earth, you take the gravitational constant, which is given over here, times the mass of the moon, the mass of the earth, over the distance between them from center to center squared. Remember, that's the hard part. Everybody forgets R. They think it's a radius. It's not. If you have Mars, okay, and the earth, you go from center to center. That's R. So remember, it's the radius of Mars plus the radius of the earth plus the distance between. That's what R is there. It's the most common mistake you see with this formula, okay? R is not just a radius. It's the distance from center to center. Okay, center to center. Same thing right here. This is the period of the orbit. R is the distance from the center of the central object to the satellite. So, for example, if here's the Earth, here's the Moon, and you want to find out the time period it takes the Moon to revolve around the Earth, which is around 28 days, that's a lunar month, that's where the month comes from. So the time period for the Moon to revolve around the Earth is the distance between them cubed, but again, from center to center. Okay, center to center, over GM. G is the gravitational constant. What is M? Of which object, though? The central, very good, which happens to be the Earth. So if it's the Sun and the Earth, then what's the central object? The Sun. So remember, this mass here is the central object. Do you see what I mean, by the way, about how you study the formulas? And it kind of explains all the stuff we've done? So all these come into play here. A central object. Next. This one here is the same variables again. Distance between the two objects. The mass of the central object, gravity. Vt is just the velocity of the orbiting object. Okay? Orbital speed. So, this would be the velocity of the moon in this case. Okay, the velocity of the orbital object, whatever that happens to be. Okay? Could be the Earth, could be the Sun. Could be the moon, sorry, depending on where it is. What is this? This is a big one that we did a lot on, a real lot on this. What did tau represent? Torque. Torque. Okay, the torque on the object. Remember, the torque is the force applied times the distance from the central axis or the lever arm. The central axis, rotating axis. Yes, so, what was our example here? Remember this? With the door? If I want to close the door, would I ever push from here? So what's happening? Look how hard I have to push. Just to keep the door shut. Because there's no distance between the rotating axis and the force I'm applying. But if I apply force here, isn't there a lot of distance now? So this force here is going to apply a lot easier, much more torque on it. What kind of a wrench do we look at? Like a lever or just a torque wrench. Torque. So remember, if you have a little wrench like this and you want to loosen a bolt, you're going to have to apply a lot of force. But if you take a wrench that's like this long and put it on a bolt, you don't have to apply much force. That's why the firemen, when they come to open the fire hydrant, ever seen that thing? It's like this big. They take the lever or whatever, the torque wrench, they put it on the fire hydrant, just push down easily, and it opens it up. Also, another good example, bolt cutters. You know what bolt cutters are? Bolt cutters. So, for example, maybe a week ago, there was a junior that couldn't get into his locker. It just wasn't open. The lock wasn't working. So I called Julio. You know who Julio is, everybody? Guy who knows what I mean?
The breaker.
Oh, I was thinking this.
We call him
Julio, the gentleman that does all the maintenance around here. Not Julio Orlando.
It's the house. It's how we call him the breaker.
Right, because he breaks all the
He's trying to fix it.
Y'all break them.
So, yeah, he does a lot of work. Last week, I called him and asked him to bring over the bolt cutters because here's what it looks like. Okay, this is just another good application. A normal thing, like, let's say, okay, normal, like you go outside, you might have shears, right? Little shears. So you go outside to cut the branches and stuff, right? Now imagine this, but instead of being handheld, it's like this long. Okay, and you have bolt cutters. These can cut through metal. At my dad's deli one time, I remember, there was something wrong with the outdoor lock. There's like a lock on it. You know, like a lot of stores, they put the metal down in front. They have the metal down in front of them. So there's a lock on it. So one day, he couldn't get the lock open. So he had to call a locksmith, and they came over just with bolt cutters. You know, up there. You pop it off. Okay? Bolt cuts right through a lock. Now, they make locks, obviously, that can't be broken by bolt cutters. But the idea of a bolt cutter is this. Look at the size of the lever arm. And then you have this shear at the end of it. If you apply a force here in both directions, you apply a force here, it creates a lot larger force up here. You're pushing here with a force that of long distance d. And this distance d1 is greater than this distance d2. Yes, because whatever rotates this distance is going to apply the same force here. So you're going to have a lot more torque. You're going to have a lot more torque. You have a lot more torque on the top of the wrench.
I used to always think you're supposed to laugh. You're not supposed to laugh.
Everybody else laughs. That's why it's a funny one.
I used to think I was supposed to laugh.
It's not funny at all. All right, next. This is the more recent stuff, so this should be a little bit fresher. What does rho, not P, rho stand for? Rho, think about fluids.
Oh, the debt. It's like something put in the water. It does something.
You were about to say in the beginning, the what? Density, very good. What is the density of the fluid? The density of the fluid. Little m is always what? Mass. What's big V though? Volume. Very good. Not velocity. Okay, capital V is volume. What did these have to do with? Good. The buoyancy force. Remember, this is tough. This was not an easy topic. I know that. Fluids are not easy at all. It was probably one of my hardest classes in college. Took a class in fluid mechanics. Very tough. I had a teacher who made the hardest test all year. And then we're going into the final. He's like, it's going to be very hard. Study everything. We studied, I'm not joking. I didn't study this long for most tests, but this test, like a solid 10 hours. Like, really, for the final exam, 10 hours. Most exams, I was studying like an hour. I was a kid to do with it. This test, it was insane what we were studying. We go take the final, easiest final ever. He messed with us, and he kept laughing about it. I was like, that was not fun. But the truth is, I learned so much from studying. That test, I was done in like 30 minutes. It was a 3-hour final. I was like, really? And like almost half the people in the class got like 95s on the test. We made it pretty simple, but everyone studied. So in the end, we learned so much because we all studied so much. No, this was when I was a sophomore. Sophomore fluid mechanics. Good class. The teacher's name is Q Wu. Q Wu.
I want to be a freshman.
Called him Q. He was awesome. Little Asian guy. Real smart guy.
His name is Ching Chong.
He does research, this guy Q Wu, and you know what he does? He's been on Discovery Channel a few times. He does research. He takes, his first name is Kwong, but it's hard to say, so he went by Q Wu. His last name is W. So he does research, and it's really creative. I think I mentioned it this year actually already, but his research is in biotransport theory, which studies the fluid flow of your blood and things in your body, which is very interesting to look at, because your fluid flow does not follow normal basic laws. It's a non-Newtonian fluid also. So it has these weird laws within your body. So he studies the biotransport on it. I took a grad course in his class. And then also he studies skiing and snowboarding. Studies skiing and snowboarding, and he looks at, it's very interesting. If you pick up enough velocity, you're almost like you're floating, believe it or not, when you ski. You ski with this almost zero friction layer between the ski and the snow. That's why skiers can pick up. It's like the idea of hydroplaning, but it doesn't have to do with the density. It has to do with the fact that the velocity is so high, and the snow provides like a pressure and resistance. So the friction is almost non-existent. He took skis and snowboards, and he used those as a model for maglev trains. So a maglev train is a train that runs on magnets. So imagine there's a bunch of positive magnets here and a bunch of negative magnets here. Yeah, but you think it would teleport, wouldn't it? If you take a positive magnet and a negative with enough force, they would levitate. So this is a lev train, or a maglev, magnetic levitation. So he studied skis, and he looked at the laws of skiing and applied those to magnetic levitation trains. Okay? This is the idea of modeling. You take something that's very basic and you apply it to something very complex.
Yeah, I know. I remember that we talking about. I was talking about that one time. Engineering thing. And the problem.
This summer?
No, not during the summertime. It was this year though. Like later on. And we were talking about that. And the problem. They said the problem would be like when you like the levitation part. Like not the problem stopping. It's just like when you stop, everything is like. Because you know how magnets they separate this boom. And so like you don't know like they gotta control how high the thing is. They be stopping, it's gonna drop, like the train's gonna drop. You can't have like 1,000 people just
The problem is control. You're absolutely right. Absolutely. Magnetism is such a strong force, and to harness it still is very difficult still.
Yeah, they say maybe impossible to control the whole magnetic force. Yeah,
it's not, and the ones that they have, the high-speed trains, are not all maglevs. They have other things involved, and then they keep that control, like thrusters and such. Okay. Next, P. What does this P stand for?
Oh.
Not power. Pressure. There's your Q there, Byron. We said it before. Take your streets. Pressure. Now remember, what was the example I did? The most basic example to remember for a scenario with pressure. How it's related. What did I do in class?
Oh, the little thing with samples of air.
There is a penny thing.
That's point force. Point force. That's doing something. What did I do, guys? I did it myself.
It sounds like if you increase the area. Oh, you stood on your foot.
Thank you. There it is. Good memory. Remember, you're standing on both feet. There's not much pressure on your tendons. But the minute you stand on one foot, there's a lot more pressure, right? And you try to lift up on that foot, and then it's like, oh gosh, it's going to be tough to balance, right? A lot more pressure there. So the idea is that if you have less area, there's more pressure. More pressure. That's why, this is the reason it works. Have you ever heard of somebody that got their tire slashed?
Yeah.
If you take a knife to a tire, it's such a very small, fine point, right? And you apply that lot of force on it, it creates a lot of pressure because it's on a small amount of area. But if you took like this book and hit the tire with it, is it going to puncture? I mean, it's not sharp, one, but there's also not much pressure. Okay? All right, we'll finish up the last ones next week. Okay, again, Monday, we'll take that practice CRN exam.